right, guys, so we are going to look at chapter 16 this week. Now, last week we were looking at random variables, but we were looking at discrete random variables. You should remember from probably about grade 8, we looked at the difference between continuous data and discrete data. So discrete data can take on only certain values, such as how many siblings do you have? You can only really say to that question, I've got 1, I've got 5, I've got 0. Discrete data can only be certain values. Continuous data means that we can give you a range and you can have any value in that range is a logical response. So how tall are you? You could be like 120.4. You could be 176.82. You know, like you can have any number in a range. So last week we were looking at discrete random variables, and this week we're looking at the maths behind continuous random variables. Okay, what that looks like is a probability density function. So we'll just have a little look. Okay, I'm just scared to make this go into project mode, so I'm just going to go not project mode. I think my computer will not like it. Okay, so a continuous random variable can have an infinite number of possible values. Can we think, other than height, can you think of another variable that's continuous? Age? Okay, but usually when you ask how old are you technically is continuous, but normally you'd be like, I'm 16, I'm 17, I'm 18. Like after you're like 7, you stop saying I'm 7 and 3 months and 2 days. Or 7 3/4. So let's think of something else. Weight. Weight is a good one. Good. What else? Come on, continuous data. Length, time. Good. How long something is, how fast something is, or how much time it takes for something to occur. Good. Now, for a continuous random variable, remember last week we did a lot of this for discrete. We said, well, what's the probability that x being our random variable equals a number? We said, what's the probability of getting 3 successful kicks in this footy game? What's the probability that x equals 3? Or we said, what's the probability of getting 2 heads on a coin toss? What's the probability of x equals 2? For a continuous random variable, the probability of that random variable taking on a specific value is 0. So it says, for a continuous random variable, the probability that that variable takes on any specific value is 0. So that's saying the probability that x equals little x, random variable for capital X, event for little x, is not going to work. So for example, if we're talking about how long it takes you to run 100 meters, that is going to be, what's a reasonable range for running 100 meters? What do you think the min to the max might be reasonably? Okay, what's the fastest? It's like 9.5, right? 9.8 or something. I don't know. What does Bolt run it in? Let's say 9 seconds. And what's the slowest reasonable amount? A minute? Okay, no, but reasonable. 100 meters. 27 seconds. I'd say a minute. Somewhere between 9 seconds and 60 seconds. Now, for a continuous random variable, if I said find the probability that the time taken equals 20 seconds, exactly 20 seconds, you would just respond and say that probability is 0. It is impossible for it to take on a particular value. Instead, what we're going to do, I know you're like, what, miss, if I run, I can get 20 seconds on the dot. It's going to instead fall in some sort of range of values. We are actually going to find the probability that somebody runs between 15 seconds and 25 seconds or something like that. The reason for that, can anyone think of why that might be? Have a go, George. No? What do you guys think? What might be a reason for that? Yeah, there's always some sort of error to our calculation. There's always some sort of accuracy, limits of accuracy that we need to consider for continuous data. So, PDF, we're not talking about a document type. PDF stands for probability density function, and that is what we're going to be using for continuous random variables. So, imagine, anyone a fan of a quarter pounder at McDonald's? They're pretty delicious. If you haven't tried one, I would strongly recommend. Right, so a quarter pounder. What is a quarter pounder? They say that you have 0.25 pounds of meat in a hamburger, right? Do you think that every single quarter pounder you get is going to have 0.25 pounds of meat in it? No. So we might be looking at, we pick up one burger and it weighs 0.23 pounds. We pick up another burger and it's 0.27 pounds of meat. So you might be interested in saying, well, tell me what the probability that you randomly select a burger and the amount of meat in that burger weighs somewhere between 0.2 and 0.3 pounds. Now I want a quarter pounder. It's not even 9 o'clock. It's never too early for a quarter pounder. All right. So, no. I mean, I'm not eating one. I'm just saying I could go a quarter pounder.
Has a fairly healthy relationship with junk food, to be honest.
I've got a good relationship with junk food. I'm just saying quarter pounders often hit the spot.
I feel like you are more than able to have one at that time.
It'll be fun. All right, so that's what we would be looking at. Would I ever be solving, hey, what's the probability that x equals 0.25? No, we already know that that's going to be 0. So instead we would be looking at, well, if I randomly select a quarter pounder, what is the probability that the amount of meat in that quarter pounder is somewhere between 0.2 and 0.3 pounds? Okay, let's say I weigh a few quarter pounders. There we go. I've picked up a bunch of quarter pounders, and this is what my graph looks like. What would you guess this, the mode, the highest point there to be? 0.25, maybe somewhere around there, but it's going to be somewhere between, you might say 0.4 and 0.5, or 0.45 and 0.55. Sorry, 0.245, 0.255. Now let's say that's 10 or 20 burgers we've weighed. If I weigh 100, what do you think happens to this histogram? I go ahead and I weigh 100 of them. It's going to become even more like a bell curve, isn't it? So if I weigh 100, those spaces on our histogram are going to get closer and closer together. What happens if I weigh 1,000? It's going to get, we're going to get closer and closer to that bell curve distribution, possibly bell curve, and it's going to get something like that. So if I go up to an infinite number of data points, this graph is going to get closer and closer to a smooth line. So you can see this one here was quite rough. There's quite harsh jags or jig-jags, or what is the word I'm looking for? That's not the word. Quite harsh steps between them. Jig-jags, that's a cool word. Zigzags, jig-jags. This is a really good lesson to record. Hi, Mint, we miss you, and I hope you're enjoying this. And then this one here, the steps get smoother, and eventually if you had an infinite number in your sample, it would become this really smooth function. This function is our PDF. Does anyone remember from that quick glance of what PDF stands for? Wow, you guys are awesome. So,
what does PDF stand for if it's like a document?
Something document file? Don't know.
Well, I'm glad we all know the correct version of PDF anyway,
Yeah.
the one we all should know for maths.
Yeah. So have a look at that, please. We are going to, for an event, we're going to have this function, and that function is called a probability density function. Now, let's say that I wanted to find the probability between one point and the next point. We wanted to find the probability of x falling in a range. What sort of maths have we learnt that might be able to help us with that? Integration. Oh, here it comes. Let's join Unit 3 with Unit 4. Get excited. Okay. So, what I would expect you to know, here's pretty much the key ideas that we just sort of looked at there. All right. So, if we've got a function and this red line over here is representing f of x, and that f of x is our probability density function. If you wanted to find the probability that x falls between A and B, all you need to do is integrate the probability density function between the lower bound A and the upper bound B. So we will be often asking you, like, if you go and select a quarter pounder, what's the probability of it being somewhere between 0.2 pounds and 0.3 pounds? You would just integrate the PDF between x equals 0.2 and x equals 0.3. Now, what do you know about probabilities? What do they sum to? Great. So the integral from negative infinity to positive infinity of a PDF probability density function equals 1. That means the sum of all the possible probabilities has to equal 1. And we also know that probability has to be larger than 0 or equal to 0. So that point above is just saying that your probability density function is always larger or equal to 0. Okay. Any questions so far? Portable document file format. Nice. Ignore that PDF. Let's focus on this PDF. Okay, so the integral from negative infinity to positive infinity of your PDF equals 1. We need to remember that the integral of all the possible values is going to equal 1. And if you are integrating between, you're interested in a particular range, we want to just find out this value here, then you just integrate between A and B. All right, we'll go to that one in a second. So this question says, consider the function with this rule. Sketch the graph of f, show that it's a PDF, and find the probability that x is greater than 0.05. All right, so sketch. Off you go. Should be able to sketch that.
What type of function is it?
Oh.
It's the parabola. Should hear everyone in here know that. Parabola.
How are we sketching it? What are we using? What might be useful? No calculators. No calculators. Use our brains. Come on, guys. Parabolas. How do we sketch parabolas? Oh, this is not rhetorical. Talk to me. Yeah. Any ideas? Come on. Okay, you could do intercepts. Could do. Firstly, is it a happy parabola or a sad parabola? All right, good. Now, how could I find that maximum point? Where does the max occur? Oh, too much work, too much work. Stop thinking so smart. Think back to grade 11 U. Turning point, where does turning point happen? Negative b on 2a. So
So my x-intercepts are 1 and -1. What's halfway between those? 0. Sub it in. You get your maximum. We should all be able to fully factorize that as well. If you didn't see that that was a difference of 2 squares, give yourself a little tick in the shin. Kick yourself in the shin. Kick it, like, kick it, give yourself a bruise. Don't let yourself forget it. Well, you've got to remember these things. Difference of 2 squares. Okay, well, that bruise will mean you don't forget it.
all right, so you could go the factorizing route, as Miss Kinnear said, or we know that b equals 0. So that means that the turning point is going to happen at negative b on 2a, which is just at 0. And then we've got the y-intercept is when x equals 0, so that's going to happen at 1.5. So you should have enough to go 0, 1.5, that's the turning point, and then now it is piecewise, and it's saying that we're only sketching it we're only following this graph when x is between 0 and 1. So we're going to go up to 1.5, and it's going to fall down to 1, 1.5. The rest of the graph is going to be on the axis. It's equal to. Yeah, so this one can be solid, and then this one needs to be open. Yeah, but it's not just implied if you don't draw anything in. But that's fine.
Well, it's generally like when we did it, we generally showed equal to, not equal to with those.
Yeah. Okay. So we've got that sort of sketch there. Now, I want you to get your calculator out now and show me that you can sketch that on your calculator. Can you sketch a piecewise on your calculator? Can you restrict a domain on your calculator? Okay, so you sketch the first function, 1.5 minus 1.5 x squared. How do I restrict the domain for our calculator? Commas are useful. Can we find the comma? Where is it? Next to the arrow. Yep, up near the top there. It's about halfway up the screen underneath cos.
Above delete.
Yep, above delete, below cos. So you press the comma. Then we need to tell the calculator our domain. We're going to use the square brackets, which are in yellow behind the plus and the minus. So shift plus will give you the square bracket. And we want it to be that function between 0, 1, and then close off the square bracket. The next function is just y equals 0, and that should be from negative infinity. How do I get it to say negative infinity? Any ideas? Don't restrict it, pretty much. So you just don't write anything. You can just put the comma in, and it's implied that the lower end of that domain is negative infinity. And it goes up to 0, and then you press shift, and then you close those brackets off. And then we also need to do the piece on the right-hand side, which is going to have a lower bound of +1 and an upper bound of positive infinity, which means I'm just going to have square brackets. And if you sketch those 3 functions, just adjust your view window, initial should be suitable, and you can see how it is happening. If you're getting syntax error, my biggest advice to you would be to scroll through all of your functions. You might just have like a random 10 or something that you kind of accidentally typed in there.
Or your V window needs changing before you press draw. So if it ever says like unable to draw, it might be because your Y max is below your Y min or something. Right?
Or they're the same value.
Yeah, or they're the same
A lot
value.
of you change your. All right, I need to see. Can we do this?
Hands up if anybody hasn't got that on their screen and needs some help.
Right, cool. Piecewise functions, sketching. Okay, so the next one says, show it is a piecewise function. Sorry, show that it's a PDF, a probability density function. How can I show that something is a PDF? What is a characteristic of a PDF? All the values are greater than 0, that's fine, we can see that, but how can I prove that it's a PDF? What does the integral need to equal? 1. So the lower bound is going to be 0, the upper bound 1, and we are going to integrate 1.5 minus 1.5 x squared. Now, a lot of you on your IA2s, you wrote this, just like that. That's not sufficient communication. You need to be clarifying what variable you are integrating with respect to. So please make sure you've got that in there. This is not a calculator question. Go ahead and do it. Let's go, let's go. Do we remember integration? And I'll actually put up the original form of the function. I think that will give you a little bit of advice as to how I would go about integrating that function. That's the original form. Think about what you can do with constants and integrals. What should your final answer be equaling? 1. That's what you want. All right, so we factor out, I would take out that constant out the front. If you didn't, that's okay, but you're just making your life more difficult than it needs to be. Then we integrate, and then we substitute our lower and upper bounds, and we get 1. Alrighty. So if a question ever asks you to show something is a PDF, we're just asking you to integrate it and make that integral, show that that integral between the bounds equals 1. Okay, now C says find the probability that x is greater than 0.5. Probability that x is greater than 0.5. All right, this is going back to that key idea up the top. If we have an upper and lower bound for our range for our random variable, we can just integrate between those upper and lower bounds. So we are going to integrate our function, which was again 1.5, 1 take x squared with respect to x. Now it needs to be greater than 0.5, so what's my lower bound? 0.5, good. And then think about the domain of the function. What's my upper bound? Well done. With how this function is defined, the upper bound is just going to be positive 1. Yeah. Yeah, good. I heard it. Good, Sam. Sum of all the probabilities will equal 1. So the area will always add up to 1, but the domains or the integrals don't necessarily finish at 1. They may finish at 7. It will just be a different function underneath, okay? But the area under the curve will always be 1, but your integrals can be different values. Okay, so this question is asking for the probability that x is larger than 0.5. So if I draw 0.5 in, it's roughly there. The area under there, that whole green section is 1. So what would be your guess as to what the probability of x being larger than 0.5 would be? Is it going to be like 2, a half, a third, 0.3? So something a little less than a half, right? That's what our gut's telling us by looking at that diagram. Okay, we can see that if that whole area is 1, whoops, the whole area is 1, then if I am splitting that in half based on my x value, that this area to the right is going to be a little less than a half. So 0.3 is a good guess. Let's go ahead and find it. We're just going to do one more integral by hand to make sure you guys can still integrate, and then we can use calculators. So integrating by hand, please. Use the same trick as before. You can pull the coefficient out the front. Check your answer on a calculator there, please, for me. Type in the integral. Make sure you are getting the same answer. We got an answer? Yep. What do we get? Did anyone do it with fractions, or do we just hate fractions? I did fractions because I love fractions, but a lot of you probably did decimals. You have to be able to use the fraction code to come up in a text screen, right? You've got to be able to convert to the fractions and use those. Your final answer should be 5/16 or 0.3125. So good guess, Eden, 0.3. Yeah. Okay, so two things that example has just shown us. To show that something is a PDF, we integrate over its bounds and the integral should be equal to 1. And part C showed us if we wanted to find the probability of a particular range, we just restrict that bound in the integral and that will give us the probability of x being larger than 0.5. Okay, I just want to have a look at two more. One is short, this one here. Use this histogram here to estimate for me the probability that 19 is less than or equal to t, which is less than or equal to 22. Now, if we are trying to look at 19 to 22, so we go in, here's 19, up to 22. So I put the numbers in there, or Miss Kinnear put the numbers in there. So what would you do to find the probability of it being between those three? What would we do? Add them, because when we do that integration, we're just finding the area under the curve. Now, if you add those together, so it's going to be the probability that t is between 19 and 20, oops, 19 and 20, plus the probability that it's between 20 and 21, plus the probability it's between 21 and 22. It's going to be 4 plus 4.8 plus 5.6. I really don't think you're going to get a question like this, but I just wanted to demonstrate something to you. So what do we get when we add those up? 14.4. And if you're thinking, hang on a sec, that's probability. Why is my probability larger than 1? Just have a quick look at the context. It's a percent. It says the percentage of frequency. So 14.4%. Now, what do you notice in part A about that range that was given? Probability that 19 is less than or equal to t, which is less than 22. What do we notice? Yep. Okay, it says that it should include 19, but it should not include 22. So for example, we could write it as the probability that x is equal to 19 plus the probability, t is equal to 19 plus the probability that t is less than 22 and larger than 19. Do you guys agree with that? That's what that equal to means. What do we know about this here? It equals 0. For a continuous random variable, the probability of being equal to an exact point is 0. So therefore, the point I guess I wanted to make with this example is it does not matter if this was phrased like that, or it could have been phrased like this, less than or equal to t, less than or equal to 22, or we could have had equal to on the 22 and not on the 19. The probability will be exactly the same. So please do not let strictly greater than versus greater than be greater than or equal to confuse you. Okay, if there is an equal to in the inequality, it has no impact on the probability for a continuous random variable. And the reason, like if you look at this graph here, there is no way to know like what the probability of getting exactly 19 is. We can't tell because we're just given ranges. All right, last one. Suppose that the random variable x has the PDF with the rule f of x equals that for that domain. Find the value of c to make it a PDF. All right, what are we going to do? We don't know what c is. C is just a constant. We need to find it. Anyone have any ideas out there? What do we know about PDFs? Okay, something equals 1. Good. What equals 1? The area under the PDF. So what is that? The area under a curve. What do we do? Definite integral of the function, which is cx integrated with respect to x, is going to equal 1, and we need to make that a definite integral. So what is the lower bound going to be? Well done, 0, and the upper bound is 2. Okay, so we now need to integrate that. You could pull the c out if you want. It's pretty, like a linear function is pretty easy to integrate as is, so I think we'll just leave it there. So raise the power on the x and divide by 2, and then you multiply by that constant. And I'm just going to remove my equal sign at the front there because we want it to all equal 1. Between 0 and 2, we substitute in our values. When we sub in our upper value, we're going to get 4c over 2 minus 0 over 2 equals 1. So 2c equals 1, therefore c equals a half, or 0.5 if you want to go decimals, that's fine.
That's often a part A question in Mr. Bransgrove exams.
Very classic part A question.
I'm thinking back to when he wrote Maths B kind of stuff, and he just used to always, that's like a simple familiar, 2 marks at most. I would expect that in your Unit 4 internal exam. I haven't seen it, but I would expect that to come up. He loves that question.
Yeah. Okay, so now we've got that C is a half. Can you please do B and C for me? You can use a calculator. B and C, off you go. All right, so for B, we're going to integrate from the lower bound 1.5 up to the upper bound of 2. 1.5 to 2 of the function 1/2 x dx. And if you put that in a calculator, you're going to get 7 over 16. And C between 1 and 1.5. Integral 1 and 1.5. X dx equals. All right, you should have an answer for me. Hands up if you've got an answer for B. Yay. Hands up if you've got an answer for C. Oh, guys, come on. You are literally just using your calculator.
Put a half in.
Calculators, let's go.
If this was a tech active, you would write down what you are solving as the integral. You know, like Mrs. Tucker is like kind of communicating. She's saying, I'm going to find the integral between 1.5 to 2 of this function. So you communicate that, and then you say, using GDC, the probability is this.
What did we get for B, Ash? Anyone get a different answer for B? 7 on 16, I agree. Just check what numbers you put in. Yeah, come, bring it here. Did you put 1.5 and 2 on the upper and lower? 1.5 and 2, not 0 and 2? Or... No? Oh. All right, and the next one should have 5 on 16. And in terms of what you should be communicating, I guess we will say using GDC. Therefore, the probability that X is, was it just greater than? Okay, guys, just have a look at that catch, please. Make sure you have got probability of X is greater than 1.5, some sort of summary statement. And then the last one was 1 up to 1.5, and your final answer was 5 on 16.